In this video, we will solve problem 4.7 from Microelectronic Circuits, 8th edition by Sedra and Smith. The problem states, assuming that the diodes in the circuit are ideal, find the values of the labeled voltages and currents. So we have a current here and a voltage here that we need to find. So whenever you're starting these problems, you always just need to make an assumption for these two diodes, D1 and D2. Are they on or off, conducting or cut off? Now, if you're a beginner, you're going to just have to make an assumption, then solve for the current and voltage and check that it actually makes sense realistically. But I may guide your attention to D2, and notice how it's connected to this positive 3 volts and this negative 3 volts. Now, if D2 is cut off, how are you able to get to 3 volts, to negative 3 volts? Because if D2 is cut off, it will behave like an open circuit, and there's no other voltage source here to get us to negative 3 volts. So I can be pretty confident that D2 should be conducting because it's in between two voltage sources. As for D1, I usually just always assume that all diodes are conducting. Then I will continue solving and check for any contradictions. So we're going to start by assuming that both of these diodes are conducting. So I need to figure out my voltage here and my current here. Well, we notice that D1 is connected to ground, which is connected in parallel with this D2 node right here. So we can say that this node is a ground observation point, which means that at this point here, right before D2, we are also at 0 volts. So therefore, since we know the voltage here and the voltage here, we can calculate the current and the voltage gain across this resistor. So first off, let's call this current I2. And we'll say I2 is equal to 0 volts minus negative 3 volts divided by 3 kilo ohms, and that is equal to 1 milliamp. Therefore, V is equal to negative 3 volts going from here and up, plus V equals I multiplied by R, current multiplied by resistance. So that would be 1 milliamp multiplied by 3 kilo ohms, which is equal to 0 volts. So that would be our value for V. Now, I don't know the current going across this diode specifically, but I can solve for the current across this wire, right? Let's call this I1. So I1, because we know that this node here is observed at 0 volts, we can state that I1 is equal to 3 volts minus 0 volts divided by 1 kilo ohm, and that's equal to 3 milliamps. Now we know for nodal analysis that the total current entering a node has to equal the total current exiting a node. So here we have I1 entering this node, and it needs to be equal to the two currents exiting the node, which are I and I2. So therefore, I is equal to I1 minus I2, which is equal to 3 milliamps minus 1 milliamp. So therefore, our current is 2 milliamps, and our voltage is 0 volts. And let's just double check for any contradictions. So if the voltage here is 0, that means this diode, D2, is going from 0 volts to negative 3 volts, 0 to negative, high to low. So this one's good. And then for our diode D1, we're going from 3 volts across here to 0 volts to 0. So D1 is also conducting, which makes sense because it should be conducting some current. If D1 was cut off, we would not expect any current conducting. So this all checks out. Now let's solve circuit B. It's very similar to circuit A, except they just changed the values of these resistors. So again, we're going to start off with our assumptions. We'll just say that for now, D1 and D2 are both conducting. This may not be true, but we're going to solve for V and I, and we're going to check for any contradictions. So similar to last time, I'm going to start by calculating the current across this wire, which will label I2. So I2 is equal to knowing that D1 here is connected to ground. This observation point here at this node would be ground. So the voltage here will be observed as ground. So it will be 0 volts minus negative 3 volts divided by 1 kilo ohm. So this time it's 3 milliamps, which means that V is equal to negative 3 volts plus V equals I times R. So 1 milliamp, or sorry, 3 milliamps this time, times 1 kilo ohm. That is equal to 0 volts. Okay, so we've calculated a voltage here. Now, what about this current here? Label this I1. I1 is equal to 3 volts minus 0 volts divided by 3 kilo ohms, which is equal to 1 milliamp. Okay, so that means that, again, I is equal to I1 minus I2, which is equal to 1 milliamp minus 3 milliamps, which is equal to a negative current. Okay, now that doesn't make sense, does it? How could we have a current going this way to the diode? Especially if we have a positive voltage here and we have 0 volts here. This is very much contradicting the behavior of a diode. We simply can't pass current through in the opposite direction. A negative value here means that the current is actually flowing upward. But that defeats the whole purpose of a diode, which is to block current in one direction. So therefore, our assumptions at the start were incorrect. So we're going to need to redo this problem with new assumptions. Now, as I explained with the first problem, D2 is very likely conducting. Wouldn't really make sense if it wasn't. So we're going to continue with our assumption that D2 is still conducting, but let's reevaluate supposing that D1 is cut off. Cut off. Okay. So again, D1 is behaving like an enormous resistor now. So that means when we see this 3 volts here, it's going to see this 3 kilo ohms. Now it's going to see this current here. And now I can already tell you, D1, as we know, when a diode is cut off, we can immediately state that the current is 0. That's just given for a cutoff. But what about the voltage here? Well, because there's no current here, the diode's cut off, so it's like an open circuit, we can essentially just ignore this whole wire. And now what we're left with is just the single wire running down here, which means since D2 is now conducting, because we're going from 3 volts to negative 3 volts, high to low, we can calculate the entire current to be 3 volts minus negative 3 volts over 3 kilo ohms plus 1 kilo ohm, right? Because that is the composite resistance in series. And let me just grab my calculator. So that's 6 divided by 4 kilo ohms. And that is 1.5 milliamps. Let me get rid of this old information. Sorry about that. So we've calculated our new current traveling across the entire wire. So we'll just say this is our new I, right? So to calculate V, we just go back to Kirchhoff's voltage law. We'll start with this negative 3 and travel up. So V is equal to negative 3 plus I times R, 1.5 milliamps times 1 kilo ohm. And so that should be negative 3 volts plus 1.5 volts, which is equal to negative 1.5 volts. And there we go. So in summary again, this current here, this one, the one that's labeled is 0, but the current traveling across this wire is 1.5 milliamps, and the voltage here is negative 1.5 volts. So it took us a little bit of time to get here because we had to redo the problem with our new assumption, but hopefully this gives you some confidence in